Welcome back to Gabversity, where facts care not about your feelings. Lovely to see you again. So thanks to the Dome Father, we are now up and running with Gabflix. So Gabflix, check out the link in the description where you can get the archives and reruns and shots of all of the Gab channels. So Gabflix, Two Tank Frank, yeah. Gabflix for your daily Gab fix. All the channels, Gab Live, Gabversity, Gab Smacked, Gab Unsmacked, even some of them will be there, which is the highly offensive version of the channel. What up? What up, Two Tank Frank? All right, so basically the link is in the description, and I think it's like bit.ly/Gab Savant, and then you can go to Gabflix for your daily Gab fix. All right, let's get back to Gabversity. Thank you to the Dome Father. Gabarama. Alrighty, and you can get the mugs, and we'll probably have t-shirts and stuff there later. And anyway, so what we were saying before was we were saying that when you let the quantum particle go, it just disappears into nothing, basically, into this infinite wave, right? And it escapes, it turns back into the wave that it always was. It was born this way, right? So how do you find something from nothing? Well, what happens is that when you draw the infinite wave as a sum, when you draw that wave as a sum of an infinite amount of smaller waves, the equation looks almost exactly like the Fourier transformation, which we just were doing in the last lecture. And the Fourier transformation is a way to use interdimensional mathematics, I call it, which is complex analysis, right? It's a way to use that to extract out of a big wave all of the small waves. And that's just a mathematical construct which mathematicians invented. But then physicists were like, hold on, we can use that. And what's so freaky about it? You only know the most probable place it will be. This is true, you have a probability distribution. But what's even worse is that when the particle is not constrained, so when you just let it go, right, and you can't trap it anywhere, it doesn't even exist at all. Right? It's the probability that it exists is zero, right? Because it's not even a particle. It's just one wave that stretches from one end of the universe to the other, right? And we think that's more to do with quantum field theory, which I'm not going to get into now, right? So how do you find a particle, right? How can you do it? Well, what you do is that you extract, using Fourier transformation, the waves that when you add them up make up an infinite wave. It's amazing. It's amazing that mathematics, right, is more powerful than the universe itself. And that to me suggests that mathematics is outside of this universe. Well, there's a lot of reasons I think that, but anyway. So as we were saying, right, when you look at this, what do you get? Why is the sun doing this to me? He's driving me crazy. All right, so look at this. This is the Fourier transformation, which happens to look almost exactly like the what do you call it? The function of this wave number. Right, and this wave number, all of these wave numbers make up the ultimate wave, right? And we did that in our last lecture. So now we can use that. Well, now what we can do is we can use this, and watch, this is how we're going to use it. Now it's mathematics. So now what I'm going to do is we're going to leave the universe, and we're only going to talk math. So math is abstract, it's right out of the universe. And then we're going to come back into the universe, and you'll see that it works, which is insane, because without that you would not have satellites, mobile phones, you wouldn't have LCD screens, you wouldn't have batteries. It's just insane how this actually works. So we're going to go into the world of maths outside of this universe, and then come back in. All right, let's do it. So this here, all right, can also be written like this: the sum of n equals minus infinity to infinity, okay, of Cn, so it's still Cn, which is some constant, right? And that it's infinite amount of constants, right? Because that n, as you can see, gets from minus infinity to infinity. Hey, Scott. All right, and now we're going to rewrite this using Euler's formula. And Euler was another genius mathematician a few hundred years ago, and he was able to show that this complex number, which is an interdimensional number, can be represented by a combination of two waves, right? Which is this, the cosine of n pi over ax, right, plus I, which is that magic two-dimensional number, sine n pi x over a. Okay. Alright, so this is just now maths. What we've done is that is the same as that. The Cn is the same, and this we've turned into this, which is two waves, which is quite amazing. Right? This is a wave that's in another universe, another dimension, and that's a wave in this one. Right? And they're out of phase as well. It's very bizarre. It's how would it look? It would look, if you could see the other universe, or the other dimension of time, it would look something like this. Yeah. So here is, sorry, that's wrong. Yeah, now imagine that that's 3D. All right, so that's the other dimension, right? And then in this dimension, we've got like this. So it's really weird. Like one wave is going that way and one is going this way. It's opposite, sort of. They're orthogonal in a way. Yeah. Something like that, like perpendicular, like that one goes that way. But what I've drawn here is actually 3 dimensions, so that's like a 4th dimension. But it's not time. That's the parallel universe dimension. So there's lots of other universes that mimic ours in mathematics that we can't prove that exist. And all of those universes, right, it hops through there. It actually sort of looks like that, but it goes that way and this goes this way. It's very weird. Anyway, so now what we're going to do is keep going. And we're going to show you that this also equals C naught. Amazing and exciting. It is pretty crazy. What I'm going to do now is, this is an infinite sum. I'm going to break it up, okay? And I'll show you what I mean. Look at the number 2, right? I've done this before. 2 is the infinite sum of these. A half, plus a quarter, plus an eighth, plus 16th, plus 1 over 16, sorry. Right? Can't prove operative. Yes, that's right. Dot, 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 dot. Right? 1 over infinity. Right? So 2 can actually be broken up into its sum of its infinite parts, if anyone knew that. So 2 is a sum of infinite parts. So you need an infinite amount of these numbers to give you the number 2, which is pretty weird. But what you can do is you could say that 2 equals the sum from n equals 1 to infinity, okay, of all of these. So, 1 over blah, 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 right? Whatever it is, okay? It's actually, it should be 2 to the n, I think. 1 over 2 to the n, I think. I'm just doing that live, but because 2 to the 1 is 2, so that's a half. 2 to the squared is 4. 2 cubed is 8. 2 4 is 16. So it's 1 over 2 to the n. So 2 can look like this. 2 can look like this. 2 can look like this. Now, have I lost you guys? Because it'll be n equals 1 in here, and then you add it to the n equals 2, then you add it to the n equals 3, and you'll get these forever. Okay? But you could also do this. You could say it equals a half, right, plus, excellent, plus n equals 2 to infinity of 1 over 2 to the n. Now, I don't know if you noticed what I just did. So I took the half outside, which is there, plus the rest of them. So the rest of these all the way up to infinity, right, would all be this. That's it. It's just notation. Okay? So what I'm going to do is exactly what I've done here, I'm going to do here. That's all. Okay? And it's going to look like this. It's going to be C naught, which is the first one, right, plus the sum from n equals 1 to infinity. All right? This one is 1, the other one was 2, but whatever, it's the same concept, right? 1 to infinity of Cn plus C of minus n. Okay? And then cos, okay, n pi x over a. Okay, so this, so far, what have I done? I've taken C naught out, right? I've put C naught out here. And then I've taken this, which is just this part, okay? And now I'm going to do the next with this part, which is plus I, because there's that I, that magic interdimensional number, sum of n equals 1 to infinity, all right, of Cn minus C minus n, okay, sine n pi x over a. All right. So now all I've done is I've expanded this to make it look like this. And that's what mathematics does. It rearranges. It's like transformers. Transformers, more than meets the eye. All right, so you got that. And now what this is, right, this is pretty crazy because we're adding the positive and the negative. It's like a mirror image of each other. Right? So if you're adding Cn plus C minus n, what you're doing is you're actually having a branch that's gonna be all the positives, and that's gonna be all the negatives. And that's how you go to negative infinity and positive infinity, which is exactly what you had here, negative infinity to positive infinity. We just rewrote it to make it look like this. All right, now there's a reason. You're gonna see why we're doing this, just to show you how awesome and how powerful mathematics is. Excuse me, I just have to put this over the top because it's behaving badly. Okay. Now, why is that important? It's important because of this. Because what I can do is say that Cn plus C minus n, you can make that equal to just a new constant, An. Right? That's it. And then the other one, which was Cn minus C minus n, you can just call that Bn. It's just another number, because that number plus this number equals another number. And that number minus this number is another number. That's it. And so therefore, what I've done is I've made it look like this. I've now said f of x, all right, equals, all right, the sum. Oh, we've lost it. It's gone. No, it's back. The sum from n equals 0 to infinity of An sine n pi x over a plus Bn of cos n pi x over a. Now, why is that important? Because those who have done mathematics realize that we are now getting the Fourier transform. All right? We're rearranging it. So that there was simply this, right? Plus C0. Okay? We've just rewritten it. And we've been able to put it in here because when you make An 0, that's going to be 0, right? So anyway, mathematically it works out. All right? If you haven't done calculus, don't worry about it. Alrighty. So, actually I've missed one thing. One thing I slightly missed. You're lost. Yeah, you're not supposed to get this. If you haven't done advanced calculus, then this section from here to here will not make sense. Because we've left the world of physics and we've gone just into mathematics. And mathematics, all we've done is rearrange. It's like a jigsaw puzzle. We've just rearranged the pieces to make a different photo. And the different photo is made of the same pieces. So it's like this. Let me show you. Here's my pencil case, right? My pencil case, right, has got all my pens. But if I take this pen and put it over here, right, it's still the same pencil case. The only difference is now I can pull out the blue one easier. All right, so that's basically what that mathematics does. We're rearranging all of the items in the pencil case to make it easier to get the ones that were at the bottom. My brain is too slow to get it. No, that's not true. If you're not writing it out and you haven't done like a couple of years of advanced calculus, it won't make sense. The parts that do make sense are the things I said before that, where I said, like, you know, you let go of the particle and it just turns into this infinitely big wave. And so what we're going to do is make that wave a sum of smaller waves. That's all we're doing. So I don't expect anyone to get it unless you've done it, like I said, if you've done advanced calculus and you got like the top grade or whatever, then it becomes easy, because it's just language. You're just moving it around. It's like taking letters out of a word and rearranging the letters to get a different word. That's basically what we're doing. Trying to think of an example. Anagrams are good ones, like I don't know, like POTUS. I can't believe you failed math. I failed when I was in school because I was a troubled autistic little kid who didn't understand anything about anyone or life or anything else or myself. But when I went back to uni, I was able to top the uni, and I was able to correct the maths professors quite a few times, actually. Anyway, all right. Well, yeah, let me know if this is too annoying. I'm happy to stop and I can just do other lectures later on. Let me know. I don't want to upset anyone, of course. Okay. I missed an I. That's the only thing I missed. I missed an I here. More, please continue. That's a very good question, Xander Jellybean. Of course. Can it be used on frequencies? Not only can it be used on frequencies, but it is used on frequencies. In fact, I spoke about this a few scopes ago, but what it is used for, can we expand waves? You can. People use it to get digital radio. So if you have satellite radio or digital radio, right? Basically what the radio is doing is extracting a mini wave out of the whole radio wave spectrum. And it's the same with light. If you have, go Gabversity. For example, in nature, this happens all the time with rainbows. So a rainbow rips apart the light wave and gives you mini waves, the red, orange, yellow, blue, green, and violet. And so basically nature knows mathematics better than we do. Anyway, in some respect. Okay, the wind is starting to pick up, which is annoying me, so I might have to go inside. Freaking shit. Bastard. Okay. So, now, what we do, right, is that we can integrate these, right? Now, if anyone remembers, if they've done calculus, they know that an infinite sum is like doing integration, which Isaac Newton came up with, because he was an unbelievable freak genius. So what he said was that we can convert the wave into this. We can say 1 over 2a from minus a to a, okay, of f of x e to the minus in pi x over a, all right, dx, all right. So Isaac Newton came up with this notation. This is just notation, and he said that equals, right, 1 over 2a multiplied by the infinite sum, which is unbelievable. He's able to even conceptualize infinity. M equals minus infinity to infinity. Okay. Of Cm outside of the integral from minus a to a, e to the I m minus n pi over a by x dx. All right, so why is that important? Isaac Newton was able to figure this out, right? And then Fourier and all of that advanced it. So why is that important? Well, it's important because if you look at the original equation that we saw, right, there it is. Look at that. That was Plancherel who figured out this. Look at that. This K is the wave number, right? And remember, as I said, K is the wave number, which is like a fingerprint of every wave. And he's saying the set of all fingerprints, right? The set of all fingerprints of waves equals 1 over square root of 2 pi, right? From the integral from that minus infinity to infinity of this. Well, look at that. It happens to look almost exactly the same. Minus a to a is like minus infinity to infinity of this. Right? And that is really important. Right. For a couple of reasons. Now, I've said before in the past lectures that each one of these waves is linearly independent. Right? It's like you cannot make one wave from another wave. They're all unrelated. Right? So you need all of them as players to make up the full wave. And in mathematics, because they're independent, it means when you integrate, you get 0. I did this when I was down in Waterfall, if anyone wants to go back and see the Waterfall scope. All right. So, is K related to H bar with light? It is. It is actually. It depends on what K. So if you change K, if you change K, you'll get different light colors, you'll get gamma rays, you'll get different rays. That's true. But you'll also get other rays which are emitted from actual particles that are not light particles as well. All right. So I have to move around because the sun is now starting to act a bit interesting. All right. So now, where am I? Okay. What's interesting about this integral is because the waves are linearly independent, right? You can have a look here. Right, have a look at that. If they're independent of each other, that's what that shows. And so, if m equals n, right, then look what happens. If they're equal the same, then that's going to be 0. So basically the whole thing is going to be 0, right? So then you're just going to get this integral is going to equal 0 because you're going to have an infinite sum of 0. Right. All right. So if that's 0, okay, all right, then sorry, that's 1, okay. This whole thing becomes 0 if m minus n. If m is the same as n, then something take away itself is 0. So that's all going to be 0. And then e to the 0 is 1, which you learn at high school. So then the integral of 1 dx is just going to be x, right? But the definite integral of x, right, is, I'll actually do it. If m equals n, then this is going to become the integral. It's going to be 1 over 2a, right, from m equals minus infinity to infinity, okay, of Cm outside of x minus a to a. Okay. Now, what does that mean? Well, that is this, which equals 1 over 2a m equals minus infinity to infinity, all right, of Cm, all right, which is that random constant that keeps changing, okay, and you put a into here, a, and then you got to take away minus a, so minus a, all right, and that a plus a is 2a, so therefore it's going to become this. Done. You see? There it is. But remember, we also know right from the beginning that this happens to equal this. So what have we just done? We have just discovered that we figured out what Cm is. We just figured out what Cm is, which is pretty crazy. Right, so therefore, Cn, which was the original, right? We just changed because n and m are equal, right? equals 1 over 2a integral minus a to a f of x e to the minus in pi x over a dx. And that is so important, right? That is so important, because look at this. We just figured out what Cn is, right? And if you remember, Cn was this number we couldn't figure out, right? And that looks just like this. So the whole point was to figure this out so we can map it across the universe and figure out what's going on, right? So now we've figured out what Cn is. It happens to be that, okay? Which is pretty damn awesome. Because now, you don't have to get this, by the way. If you haven't done advanced calculus, this will not make sense. And that doesn't matter, because the theory is pretty easy that we've done. Like the whole point of doing this. This part's only for the mathematicians. Okay. So now what we're going to do, show me theory. Yeah, it's coming, my friend. So what we've done now is we can now say that n pi on a equals k, which is the wave fingerprint. So we're now just substituting it back into the world of physics. Now we're coming back. So as I was saying, we left the world of physics to go into mathematics, which is outside the universe, and we rearranged everything to come back and bring us an equation. And now we're going to put that equation back into the world of physics to show you how to find a particle that the laws, classical laws, will tell you does not exist. All right, let's go. Okay, equals k, and there's 3, because that means by definition. That means we are making that equal k. Okay. All right, and we're saying that f of k, all right, the transformation of k by definition is 2 over pi 2 over pi square root a cn. All right. So now the original series, all right, we're coming back, almost coming out of the world of maths into physics. So now we can say, all right, that the original series f of x equals the sum of n equals minus. Can you show when done for screenshots? Yeah, absolutely. There's a replay here, and also if you go to the Gab, there's Gabflix, and the link is in the description. You can go there and you have access to all the channels and everything else, and that's all done through YouTube videos. So you can do that. Otherwise, yeah, you can look at the replay here, no problem. So n that 2, so minus infinity to infinity, right, of pi over 2 square root, and then we've got 1 over a fk. This is still maths, by the way, so you don't have to worry about this not making sense if you're not fluent in maths. Don't worry about that. Kx, and then we have a over pi delta k. Cleaver username, Gabflix. Gabflix for your daily Gab fix. Alrighty, so we're almost out. Okay. So now what I've done, right, if you guys remember, we figured out what Cn was, right? And on the other page, Cn, and I'm going to go over this again, we're almost done, and I'll explain. So Cn equals this, right? If you remember, we figured out mathematically that Cn is this, right? So we can use that, and we can say is this. We can say that Cn is, as I said, 1 over 2a integral minus a to a, okay, of f of x e to the minus ikx dx, right? And if you guys remember, we also said that Cn equals pi over 2 square root, okay, or root pi over 2, okay, 1a f of k, which is fuck. Okay, so Cn equals a square root of fuck. Oh yeah. All right. So now we can solve for this. We can say that that equals that, and using algebra, we just get that on its own, right? So therefore, fuck equals, right? And all we're doing is putting this on that side, okay? So that will equal 1 over root 2 pi, right, from minus infinity to infinity, right? Sorry, I said minus infinity. I knew I was doing something wrong. Minus a to a, okay, of f of x e to the minus ikx dx. All right. So we've done that. This is now the Fourier transform, right? As you can see, Fourier transform. So what this means is that all of the fingerprints of the wave equals the sum, right, of all of the waves within the distance a to a. And it's in the alternate dimension. So what does that mean? That means if I have a wave that looks like this, right? Right? This section here might be 96.3 FM. This section here might be 105.7 FM. You see what I mean? But you can't see it. You can't see it. So what you do is you turn it to its side, you go whoosh, you turn it to its side, and you get an infinite sum of these things. You get that, right? It's quite amazing. So what's happened, right, to explain, is that we get the wave, which looks like that, right? And then we turn it on its side, and in this world, if you turn it on its side, it's invisible, right? Because it's a wave. How do you even look at a wave on its side? It makes no sense, right? But what you do is, using the second dimension of the parallel universe that mathematics has that we can't see, we can split them all apart. So you get each wave all lined up next to each other. And then when you turn it back flat, it looks like one wave. It's sort of like, imagine this paper, right? And then I turn it on its side, it's flat. But what I could do is bust it open so that each dot is all in a cloud, all lying next to each other. Each dot that makes up the whole page. So there's a dot there, there's a dot there, right? So, for example, you know, math is goddamn straight. So all of these dots that make up the paper, you could punch them all out and then turn it this way. And then each dot would have its own spot in space. So you'd have a whole cloud and each dot would be in one spot. And that's what that mathematics does. It rips apart that wave, turns it on the side, rips it apart, and you can see every single wave, all the mini waves that make up the big wave. And that's just mathematics, but what's interesting is that actually is exactly what happens to quantum particles. So this mathematics was discovered before quantum particles were discovered. And that's the crazy thing. All right. So all right, here we go. So look at this. That, right? Let's go all the way back to the beginning. Look at this wave function. Remember the wave function? The wave function when the particle is free is an infinite wave. But now we can split it up into its Fourier transformation. So that means that we can find all of the mini waves that make up the big wave, because that equation looks exactly like the mathematical Fourier transform, which is right here. Isn't it amazing that the laws of this universe not only exactly obey the laws of mathematics, but mathematical laws are discovered before we even find them in the universe, right? And there are hundreds and hundreds of millions of laws that that we've studied, all of us as mathematicians, that have yet not been discovered in this universe and outside of this universe. That's the crazy thing. So you blew my mind. My pleasure. My absolute pleasure. So there you go. So just to confirm what we basically did, right? What we did was we showed that when you let go of a particle and it disappears and turns into an infinite wave, you can break down that infinite wave into an infinite amount of smaller waves. And those smaller waves you can use to find the particle, right? That's how you do it. So bingo. All right, guys. Always a pleasure to talk to you on Gabversity. Don't forget, look at the link in the description. You can go to Gabflix for your daily Gabfix. Check all the replays. I don't know how it works yet. I don't know the full story. It was done by the Dome Father. You can get the pompous mugs. You can get... I think Gab Unsmacked will be there soon. That's a really offensive channel, which I'm... Yeah, you too, guys. All the best. And until next time, Gabsmacked, Gabversity, where facts don't care about your feelings.